You have been lied to, not by your teachers, not by your parents, by the very name we gave to the beginning of everything, the Big Bang. Even the word suggests an explosion, fire and fury on a cosmic scale, but there was no bang, there was no explosion, and the man who coined the term did not even believe the theory was true. Today we are dismantling 10 of the biggest lies you have been told about the universe, and what we are about to uncover will change how you see everything. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. You have been lied to, not by your teachers, not by your parents, by the very name we gave to the beginning of everything. Every science documentary you have ever watched, every textbook you have ever read, every classroom diagram you have ever seen. They all show the same thing. A tiny point, an explosion, matter flying outward in every direction like cosmic shrapnel from the greatest bomb ever detonated. The Big Bang. Even the name itself suggests violence, destruction, fire and fury on a scale beyond human comprehension. But what if the entire picture is wrong? What if the very foundation of how you understand the birth of the universe is built on a misconception so profound that it changes everything you thought you knew about reality itself? Today we're going to dismantle 10 of the biggest lies you have been told about the universe. Not conspiracy theories, not fringe science. Real documented scientific truths that contradict what most people believe. And we are going to start with the biggest lie of all, the lie that gave the universe its most famous moment. The Big Bang. By the time we reach the end, you will understand why black holes do not actually suck anything, why the sun is not the colour you think it is, why space is not cold, why you have always used your entire brain, and why everything you think you know about the asteroid belt comes from science. Fiction writers who never consulted a single physicist. But first, the explosion that never happened. 13.8 billion years ago, something extraordinary occurred. The universe began. Every star, every galaxy, every atom in your body, every thought you have ever had, everything that exists or will ever exist traces back to this singular moment. And for nearly a century we have called this moment the Big Bang. An explosion, a detonation, the ultimate firework. Here is the problem. There was no bang, there was no explosion. And the man who coined the term did not even believe the theory was true. The year is 1949. A radio studio in London. A physicist named Fred Hoyle sits before a microphone preparing to explain cosmology to the British public. Hoyle is brilliant, controversial, and deeply skeptical of the idea that the universe had a beginning. He prefers a different theory, the steady-state model. A universe that has always existed and will always exist. No beginning, no end. Just eternal cosmic stability. But there is a competing theory, one proposed by a Belgian priest and physicist named Georges Lemaitre 2 decades earlier. Lemaitre suggested that if you run the expansion of the universe backward like rewinding a film, everything converges to a single point. A primeval atom, he called it. The cosmic egg from which all of creation hatched. Hoyle needs a way to describe this competing theory to his radio audience. He needs something memorable, something that captures the absurdity he sees in the idea, so he calls it the Big Bang. One big bang at a particular time in the remote past. The phrase sticks, it spreads, it becomes the standard term for the origin of the universe, and it plants a completely false image in the minds of billions of people for generations to come. Here is what most people picture when they hear Big Bang. A tiny point suspended in darkness, an explosion, matter flying outward in all directions like debris from a bomb, the universe expanding into empty space the way smoke expands into a room. This image appears in documentaries, in textbooks, in museum exhibits, in the imaginations of children staring up at the night sky wondering where it all came from. This image is completely wrong. First and most importantly, the Big Bang was not an explosion of matter into space. It was an expansion of space itself. This distinction is crucial, and it is where most people go wrong. In a normal explosion, debris flies outward from a central point into a surrounding environment. There is a before and an after, a center and an outside. The explosion happens in space and spreads through space. The Big Bang did not happen in space. The Big Bang created space. There was no surrounding environment for matter to fly into. There was no empty room waiting to be filled. There was no outside. There was no before. Space and time themselves began in that moment. The expansion was not matter moving through space. The expansion was space itself stretching, growing, carrying matter along with it like dots painted on a balloon that is being inflated. Imagine drawing dots on a deflated balloon. Each dot represents a galaxy. Now inflate the balloon. What happens? The dots move apart from each other, but they are not moving through the rubber. The rubber itself is stretching. Every dot sees every other dot moving away. And here is the key insight. There is no center. No dot can claim to be at the middle of the expansion. Every dot sees itself as stationary while all other dots recede. This is exactly what we observe in the real universe. Every galaxy sees every other galaxy moving away from it. The farther away a galaxy is, the faster it appears to recede. This is not because galaxies are flying through space like debris from an explosion. It is because the space between galaxies is expanding. The fabric of reality itself is stretching. Second, there was no bang, no sound. Sound requires a medium. Molecules vibrating against each other. Compression waves travelling through air or water or solid material. In the earliest moments of the universe, there were no molecules, no atoms, no air, nothing that could carry a sound wave. The universe began in utter silence, a silence so complete that the word silence barely captures it. There was nothing to be quiet in the first place. Third, and this one truly breaks intuition, the Big Bang did not happen at a specific location. It did not occur somewhere out there in space where we could point a telescope and say, there, that is where it all began. The Big Bang happened everywhere. Every point in the universe was the center. Every point in the universe was the origin. The expansion began at every location simultaneously, because every location is descended from that primordial state. Think about that for a moment. You're standing at the exact spot where the Big Bang occurred. So is everyone else on Earth. So is the most distant galaxy we can observe. There is no center to find because everywhere is the center. The expansion did not spread out from a point. It occurred at all points at once. This is why the observable universe looks roughly the same in every direction. Galaxies are distributed more or less evenly. The cosmic microwave background radiation, that faint echo of the early universe, has nearly identical properties no matter which direction we look. If the Big Bang had been an explosion from a central point, we would expect to see asymmetries, denser regions in one direction, emptier regions in another, a detectable center somewhere out there. We see none of that. What actually happened in those first moments is more subtle and more magnificent than any explosion could be. The universe began in an unimaginably hot and dense state. Not a tiny ball floating in empty space, but a condition where space itself was compressed. Temperatures were so extreme that the four fundamental forces of nature were unified into a single force. There were no atoms, no protons or neutrons, just a seething plasma of energy and particles that cannot be described by any physics we fully understand. Then came expansion. Not an outward rush of debris, but a rapid stretching of the very fabric of space-time. In the tiniest fraction of a second, the universe underwent a period called inflation. Space expanded faster than the speed of light. Not because anything was moving faster than light through space, which is impossible, but because space itself was growing. There is no speed limit on the expansion of space, only on objects moving through space. During inflation, the universe grew by a factor of at least 10 to the 26th power. That is a 1 followed by 26 zeros, a region smaller than a proton ballooned to the size of a grapefruit in roughly 10 to the minus 32 seconds. Then inflation ended. The expansion continued, but at a slower rate. Energy converted into matter. The first quarks appeared, then protons and neutrons, then nuclei, then atoms, then stars, then galaxies, then you. The evidence for this picture is overwhelming. We can see the cosmic microwave background radiation, light released when the universe was only 380,000 years old. We can measure the abundances of hydrogen and helium, which match exactly what the Big Bang model predicts. We can observe the expansion of space directly by measuring how distant galaxies are moving away from us. Every piece of evidence points to the same conclusion. The universe began in a hot, dense state and has been expanding ever since. But none of that evidence points to an explosion. The evidence points to expansion, to stretching, to growth. The Big Bang Theory describes the evolution of the universe from a starting density and temperature that is well beyond humanity's capability to replicate. It does not describe how energy, time, and space were caused. It does not describe an explosion in the conventional sense. It describes something far stranger and far more beautiful, and yet the name persists. Big Bang. Two words that conjure exactly the wrong image. Two words given to us by a skeptic who thought the whole idea was ridiculous. Two words that have misled generations into thinking of the birth of the universe as some kind of cosmic bomb. There have been proposals to change the name. Some scientists have suggested calling it the Everywhere Stretch. Others have proposed the initial expansion or the Great Emergence. None of these have caught on. The Big Bang is too embedded in popular culture, too memorable, too evocative. Even scientists who know better continue to use the term for convenience. The irony is profound. Fred Hoyle coined the phrase Big Bang to mock the theory. He lost the scientific debate decades ago. The steady-state model he championed was abandoned when evidence mounted for a universe with a beginning. But his mocking phrase survived. The name he intended as a dismissive label became the standard terminology for the most successful cosmological model in history. So the next time someone asks you what the Big Bang was, tell them the truth. Tell them it was not a bang, not an explosion, not debris flying through empty space. Tell them it was the emergence of space itself, the stretching of reality, the silent birth of everything from a state beyond our comprehension. Tell them the most important moment in the history of existence has been misnamed for nearly a century. Tell them the first great lie about the universe is written into the very name we gave its beginning. But this is only the beginning of our journey through cosmic deception. Because if you think the Big Bang misconception is shocking, wait until you learn what black holes actually do. Spoiler alert, they do not suck, not even a little bit. Chapter 2. Black holes do not suck. Picture this. A dark void in space, a swirling vortex of destruction. Matter spiraling inward like water down a cosmic drain. Everything that comes near gets pulled in, absorbed, consumed, gone forever. This is the image of black holes that dominates popular culture. Cosmic vacuum cleaners, gravitational monsters, the ultimate predators of the universe lurking in the darkness waiting to devour anything foolish enough to stray too close. Hollywood loves this version of black holes. Science fiction writers adore it. Even NASA has released animations showing matter being sucked into these cosmic beasts. The language we use reinforces the misconception. We say black holes suck matter in. We describe them as consuming stars and devouring galaxies. We treat them as active hunters rather than passive objects. Here is the truth. Black holes do not suck anything. Not even a little bit. They have no special pulling power, no enhanced gravitational attraction, no cosmic vacuum mechanism that reaches out and grabs passing matter. The biggest myth about black holes is that they suck, and it is time we finally put this lie to rest. To understand why this misconception exists and why it is wrong, we need to start with what a black hole actually is. A black hole is simply an object so massive and so compact that the escape velocity at its surface exceeds the speed of light. That is it. Nothing more mysterious than that. If you compress enough mass into a small enough region, space-time curves so severely that nothing can climb out of the gravitational well. Not matter, not radiation, not even light itself. The boundary at which escape becomes impossible is called the event horizon. Cross this threshold, and you're not coming back. Everything inside the event horizon is causally disconnected from the rest of the universe. Information cannot escape. Signals cannot be sent. The interior is sealed off from everything outside. This sounds terrifying, and it is if you cross the event horizon. But here is what most people misunderstand. The event horizon is not a physical surface. It is not a wall or a barrier or a mouth that opens to swallow passing spacecraft. It is simply a mathematical boundary, a point of no return defined by the geometry of space-time around an extremely massive object. Outside the event horizon, a black hole behaves exactly like any other object with the same mass. This is the crucial point that demolishes the sucking myth. If you replaced our sun with a black hole of equal mass, what would happen to Earth? Would we be sucked in? Would our planet spiral to its doom? Would all life be extinguished in a cosmic feeding frenzy? No. Earth would continue orbiting exactly as it does now. The gravitational force acting on our planet would be identical because the mass is identical. The only difference would be the loss of sunlight. We would freeze in the darkness, but we would not be pulled into the black hole any more than we are currently being pulled into the sun. Think about that for a moment. A black hole with the mass of the sun would have an event horizon only about 3 kilometers across. Earth orbits roughly 150 million kilometers from the sun. At that distance, the gravitational influence of a solar mass black hole would be completely indistinguishable from the gravitational influence of the sun itself. No sucking, no enhanced pulling, just ordinary gravity acting at ordinary distances. This extends to all scales. The supermassive black hole at the center of our Milky Way galaxy contains about 4 million times the mass of the sun. It sounds apocalyptically dangerous. Yet our solar system orbits the galactic center at a comfortable distance of roughly 26,000 light-years. We are in no danger of being sucked in. Stars much closer to the galactic center orbit that black hole the same way planets orbit stars. Some have been observed whipping around the black hole at tremendous speeds, completing their orbits in just a few years. They do not spiral inward. They maintain stable orbits, because black holes do not suck. So why does the sucking myth persist? Part of the reason is language. When we describe gravity, we use words like pull and attract. These words suggest an active process, something reaching out and grabbing. But gravity does not work that way. Gravity is not a force in the Newtonian sense of something pushing or pulling. In Einstein's general relativity, gravity is the curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. The bowling ball creates a depression, a dimple in the fabric. If you roll a marble across the sheet, the marble curves toward the bowling ball not because the bowling ball is pulling it, but because the marble is following the curved surface. It is moving along the straightest possible path through curved space. Black holes create extreme curvature, the deepest gravitational wells in the universe, but they do not reach out and grab anything. Objects fall into black holes the same way they fall into any other gravitational well, by moving through curved space-time. The black hole does not suck. Objects simply fall. Another reason for the misconception is the imagery we see of black holes consuming matter. When a star passes too close to a supermassive black hole, it can be torn apart by tidal forces. The stellar material forms an accretion disk, a swirling ring of superheated gas spiraling inward. We see dramatic images of this material glowing as it falls toward the event horizon. It looks exactly like something being sucked down a drain. But look more carefully at what is actually happening. The star did not get sucked in by some special black hole force. It ventured too close and was torn apart by the differential in gravitational force between its near side and its far side. These are called tidal forces, the same phenomenon that causes ocean tides on Earth. The moon does not suck the oceans toward it. The gravitational pull on the near side of Earth is slightly stronger than on the far side, which stretches the ocean slightly. Black holes produce extreme tidal forces because their mass is concentrated in such a small region. Get too close, and the difference in gravitational pull between your head and your feet would stretch you into a thin strand like spaghetti. Physicists actually call this spaghettification. It is not a pleasant way to die, but it is not being sucked in. It is being stretched by differential gravity. The accretion disk forms because matter rarely falls straight into a black hole. Most matter has some angular momentum, some sideways motion. This causes it to orbit rather than plunge directly in. Friction within the disk heats the material and causes it to slowly lose orbital energy, spiraling inward over time. Eventually, some of the matter crosses the event horizon. But this process can take millions of years. The black hole is not actively pulling the material. The material is losing energy through friction and gradually falling deeper into the gravitational well. In fact, most of the matter in an accretion disk never falls into the black hole at all. Powerful magnetic fields thread through the disk. Friction heats the gas to millions of degrees. Enormous jets of material blast outward from the polar regions at nearly the speed of light. A black hole can actually eject more matter than it consumes. Some of the most luminous objects in the universe are quasars, supermassive black holes with such active accretion disks that they outshine their entire host galaxies. These black holes are not just consuming matter, they're converting gravitational energy into radiation and particle jets with tremendous efficiency. Here is another way to think about it. If black holes really sucked everything nearby into them, the universe would look very different. Black holes have existed for billions of years. Some formed shortly after the Big Bang. If they were cosmic vacuum cleaners, they would have grown without limit. They would have consumed their host galaxies. They would have merged and grown and consumed more galaxies. Eventually, there would be nothing left but black holes. Instead, what do we observe? Black holes in stable equilibrium with their surroundings. Stars orbiting them in regular patterns. Entire galaxies hosting supermassive black holes at their centers without being consumed. The Milky Way has been orbiting our central black hole for over 10 billion years. We are not being sucked in. We are not even falling toward it. We are in a stable orbit like every other star in the galaxy. The gravitational influence of a black hole diminishes with distance exactly the same way as any other massive object. Double your distance from a black hole, and the gravitational force drops to 1/4. Triple your distance, and it drops to 1/9. At sufficient distances, the gravitational influence becomes negligible. A black hole on the other side of the galaxy might as well not exist as far as our solar system is concerned. This is why you should not worry about black holes threatening Earth. The nearest known black hole is several thousand light years away. Even if it were somehow heading directly toward us, which it is not, the gravitational influence at that distance is immeasurably small. For a black hole to affect Earth, it would need to enter our solar system. And even then, it would only be dangerous if it came close enough to disrupt planetary orbits. At the distance of Neptune, even a stellar mass black hole would have minimal effect on the inner solar system. There is one more aspect of black hole physics that feeds into the sucking myth: the event horizon itself. Once you cross it, there is no escape. This sounds like the ultimate act of cosmic consumption, a one-way door to oblivion. But think about what this actually means. The event horizon is not a physical barrier that grabs you and pulls you in. If you were falling toward a black hole, you would cross the event horizon without feeling anything special. There is no wall to hit, no force that suddenly switches on. You would simply continue falling, following the curved geometry of space-time until tidal forces eventually tore you apart. For a supermassive black hole, you might not even notice crossing the event horizon. The tidal forces at the horizon can be quite mild if the black hole is massive enough. The inescapability of the interior has nothing to do with being sucked in. It has everything to do with the structure of space-time. Inside the event horizon, all paths through space-time point toward the singularity at the center. Moving away from the singularity would be like trying to move backward through time. It is geometrically impossible. You are not being pulled toward the center. All futures lead there. So let us finally put this myth to rest. Black holes are not cosmic vacuum cleaners. They do not suck matter into their hungry maws. They do not reach out and grab passing spacecraft. They do not threaten to consume the galaxy. They are simply objects with such extreme mass concentration that light cannot escape from their immediate vicinity. Beyond that vicinity, they behave like any other massive object. Their gravity attracts. Objects fall toward them. But sucking implies an active process that simply does not exist. The universe is strange enough without adding fictional dangers. Black holes are genuinely fascinating objects. They mark the boundaries of our understanding of physics. They create conditions where space and time behave in ways we barely comprehend. They harbour the deepest mysteries in cosmology. But they are not the monsters that popular culture has made them out to be. And speaking of things that are not what popular culture has made them out to be, let us talk about something even closer to home, that giant ball of light that rises every morning. The one you have drawn as yellow since kindergarten, the one that appears golden in every sunset photograph. The sun is not yellow. It never has been. And the reason you think it is reveals another lie that runs so deep most people never think to question it. Chapter 3. The sun is not yellow. Close your eyes. Picture the sun. What colour do you see? Yellow. Of course it is yellow. Every drawing you made as a child featured a yellow circle with triangular rays emanating from its edges. Every emoji, every logo, every cartoon, yellow sun, golden orb, warm amber light streaming through windows. The sun is yellow the same way the sky is blue and grass is green. It is one of those facts so fundamental that questioning it seems absurd. Except it is wrong. The sun is not yellow. The sun has never been yellow. If you could travel into space beyond Earth's atmosphere and look directly at the sun without damaging your eyes, you would see something quite different from the golden disk you imagine. You would see white, pure, brilliant, blinding white. The sun's true colour is the absence of any single colour. It is all colours combined. The sun is white. This misconception runs so deep that even astronomers perpetuate it. We call stars like our sun-yellow dwarf stars. This classification system dates back over a century and refers to surface temperature rather than actual colour. The sun sits in the G-type category on the stellar classification chart. G-type stars are sometimes called yellow because they are cooler than blue stars and hotter than red ones. But the name is misleading. A G-type star viewed from space appears white, not yellow. So why does the sun look yellow to us on Earth? Why does every photograph of a sunny day show golden light? Why do sunsets paint the sky in reds and oranges? The answer lies not in the sun itself, but in the thin layer of gas surrounding our planet. The atmosphere is lying to you every single day. Sunlight is not a single colour. It is a mixture of all visible wavelengths: red, orange, yellow, green, blue, violet. Every colour of the rainbow combined into a single beam. When you pass sunlight through a prism, it spreads into its component parts. This is because different wavelengths bend by different amounts when they enter a new medium. The prism reveals what sunlight actually contains, all colours. And when all those colours combine, the result is white. When sunlight enters Earth's atmosphere, something happens. The gas molecules that make up our atmosphere scatter light, but they do not scatter all wavelengths equally. Shorter wavelengths, the blue and violet end of the spectrum, scatter much more easily than longer wavelengths. This is called Rayleigh scattering, named after the physicist Lord Rayleigh, who first explained it mathematically in the 19th century. As sunlight passes through the atmosphere, the blue light bounces around in all directions. It hits one air molecule and scatters, then it hits another and scatters again, and again, and again. Eventually this scattered blue light fills the entire sky, which is why the sky appears blue during the day. The blue has been extracted from the direct sunbeam and spread across the entire dome above your head. What remains in the direct sunlight that reaches your eyes? With some of the blue removed, the balance shifts. The light that has not scattered contains proportionally more of the longer wavelengths, red, orange, yellow. This shifts the apparent colour of the sun toward the warm end of the spectrum. At noon, when the sun is high overhead and the light passes through the minimum amount of atmosphere, the shift is subtle. The sun appears only slightly yellow. You might describe it as white with a warm tint. But at sunrise and sunset, the effect becomes dramatic. When the sun is near the horizon, its light must travel through far more atmosphere to reach your eyes. The path length might be 10 or 20 times greater than at noon. More atmosphere means more scattering. More blue and green light gets removed. By the time the light reaches you, almost all the short wavelengths have been stripped away. Only the longest wavelengths remain. Red, deep orange. The spectacular colours of sunset are not coming from the sun. They are what is left after the atmosphere has taken its share. This means every photograph of a yellow sun is actually a photograph of atmospheric distortion. Every painting, every emoji. We have been documenting not the sun's true appearance, but the effect of looking at the sun through a filter, and that filter is the very air we breathe. Astronauts have confirmed this. When you leave Earth's atmosphere, the sun transforms. Gone is the friendly yellow disk of childhood drawings. In its place is a blazing white furnace. Photographs taken from the International Space Station show the sun as white against the black background of space. Astronauts describe being unable to look at it directly even with heavy filtering because of its intense white brilliance. The distinction matters because the sun's colour tells us something fundamental about its temperature. Stars emit light based on their surface temperature. This relationship was discovered in the 19th century and follows what physicists call blackbody radiation. The hotter an object, the more its light shifts toward the blue end of the spectrum. The cooler an object, the more it shifts toward red. Our Sun has a surface temperature of roughly 5,780 Kelvin. At this temperature, the peak of the Sun's emission actually falls in the green portion of the visible spectrum. Yes, green. If you measured the intensity of light at each wavelength, you would find that the Sun puts out slightly more green light than any other colour. So why does it not appear green? Because the Sun emits across the entire visible spectrum, not just at its peak wavelength. The green peak is surrounded by strong emission in yellow, red, blue and violet. Your eyes do not see the peak, they see the mixture, and when you mix all those colours together, including green, red, blue and everything in between, the result is white. There are no green stars in the night sky for exactly this reason. A star hot enough to peak in the green portion of the spectrum also emits enough red and blue to wash out the green. All such stars appear white or white with a very slight tint. The Hertzsprung-Russell diagram, which astronomers use to classify stars by temperature and luminosity, often shows stars in different colours, but these are representational colours, artistic choices to make the diagram easier to read. Real stellar observations show something simpler. Hot stars appear bluish-white, cool stars appear reddish, stars in between, including our Sun, appear white. Consider what this means about our perceptions. We have an emotional relationship with the colour yellow. It represents warmth, cheerfulness, summer days. We associate it with the Sun because we have always seen the Sun as yellow, but this association is based on an atmospheric illusion. The real Sun, the fusion reactor at the centre of our solar system, cares nothing for warmth or cheerfulness. It is a white-hot ball of plasma converting hydrogen into helium and flooding the solar system with radiation. Yellow is a story our atmosphere tells us, not the truth. The misconception has practical consequences. When lighting designers and cinematographers try to simulate sunlight, they often reach for yellow gels and warm filters. This creates the familiar golden look we associate with sunny days. But actual midday sunlight is much more neutral. The yellowness we perceive comes from contextual cues and atmospheric filtering, not from the light itself. Photography color correction software includes presets for daylight. These presets assume a color temperature of around 5,500 Kelvin. Bright, neutral, white. This is the color of unfiltered sunlight. Photographers know this. They calibrate their white balance to sunny conditions and get neutral colors. The yellow Sun lives only in our uncorrected perceptions and our artistic representations. Look at the night sky. Find Sirius, the brightest star visible from Earth. Sirius appears blue-white, with a surface temperature of nearly 10,000 Kelvin. Now find Betelgeuse, the red supergiant in Orion's shoulder. Betelgeuse appears distinctly red, with a surface temperature of only 3,400 Kelvin. Between these extremes lie white stars like our Sun. Not yellow, not orange, white. The classification of our Sun as a yellow star has more to do with historical naming conventions than visual reality. There is a certain melancholy in this revelation. The yellow Sun has been with us since childhood. It represents comfort and familiarity. Learning that it was never really yellow feels like losing a small piece of innocence. But there is also wonder in the truth. The Sun is not a friendly yellow companion. It is a white-hot thermonuclear furnace 4 million times the mass of Earth, generating the equivalent of 100 billion nuclear bombs every second. Its true color reflects its true nature. Brilliant, blazing, utterly inhospitable, and beautiful in a way that yellow never quite captured. The next time you watch a sunset, remember what you're actually seeing. You are watching Earth's atmosphere strip away the blue and green components of white sunlight, leaving only the longest wavelengths to reach your eyes. The red and orange colours are not coming from the Sun. They are the signature of scattered light, the visible evidence of our atmosphere at work. The Sun itself, hidden behind the atmospheric veil, remains white, eternal, unchanged. We live on a planet that lies to us about the colour of our star. That seems strange until you realise it lies to us about many things, including temperature. Because if you think space is cold, if you imagine the void between the stars as a freezing wasteland where exposed astronauts would instantly turn to ice, you have been deceived yet again. Space is not cold. In fact, in the most important sense, space has no temperature at all, and understanding why reveals one of the most profound misconceptions about the universe most people carry with them their entire lives. Chapter 4. Space is not cold. Picture the scene, a science fiction movie. An astronaut's suit tears. They are exposed to the vacuum of space. Within seconds, frost creeps across their skin, ice crystals form on their eyelashes, their body freezes solid in moments, preserved in eternal cold. This image appears so often in movies and television that it has become an accepted truth. Space is cold, the ultimate cold. Step outside without protection and you will freeze instantly. This is wrong. Dramatically, dangerously, fundamentally wrong, and the misconception runs so deep that even educated people repeat it without thinking. Space is not cold in the way we imagine cold. Space is not cold in the way Earth is cold. In the most important physical sense, space is not cold at all. To understand why, we need to rethink everything we believe about temperature. What is temperature? Most people would say it is a measure of hot and cold. Something is warm or cold and temperature tells us how much. But physicists define temperature more precisely. Temperature is a measure of the average kinetic energy of particles. The faster the atoms and molecules in a substance are moving, the higher its temperature. The slower they move, the lower the temperature. Temperature describes motion at the atomic level. Here is the critical insight. Temperature requires particles. No particles, no motion to measure. No motion, no temperature. A perfect vacuum containing absolutely nothing has no temperature. Not cold, not hot. Temperature is simply undefined. The concept does not apply. Space is not a perfect vacuum. There are particles out there. Hydrogen atoms drift through interstellar space at a density of about 1 particle per cubic centimetre. In the vast voids between galaxies, the density drops even lower, 1 particle per cubic metre. But let us be generous and assume there are some particles in any given region of space. These particles are moving. They have kinetic energy. Can we measure their temperature? Yes, but the answer is not what you expect. In the regions near stars where energetic photons constantly strike whatever matter exists, those scattered particles can be extremely hot. The solar wind, the stream of charged particles flowing outward from the sun, has a temperature of hundreds of thousands of degrees. The corona of the sun, the wispy outer atmosphere visible during eclipses, reaches temperatures of millions of degrees. Space near our star is not cold, it is extraordinarily hot. But wait, if space, near the sun, is so hot, why do spacecraft need heating systems? Why do astronauts in orbit experience temperature extremes? Why does the moon's surface freeze at night? The answer reveals the crucial difference between temperature and heat transfer. Temperature tells you how much kinetic energy particles have on average, but heat transfer, the actual flow of thermal energy from one place to another, requires a mechanism. On Earth, we have 3 mechanisms for heat transfer. Conduction, where heat moves through direct contact between materials. Convection, where heat moves through the circulation of fluids like air or water. And radiation, where heat travels as electromagnetic waves. In the vacuum of space, conduction and convection essentially do not exist. There is no material to conduct heat through. There is no fluid to circulate. The only way to lose or gain heat in space is through radiation. And radiation works very slowly for objects at ordinary temperatures. Think about what this means for an astronaut exposed to vacuum. Popular imagination says they would freeze instantly. The reality is far stranger. Their body would actually have trouble losing heat. There is no air to carry warmth away, no ground to conduct heat into. The only heat loss mechanism is thermal radiation, the faint infrared glow that all warm objects emit. At body temperature, this radiation carries away energy at a rate of roughly 100 watts. That sounds like a lot until you consider that a human body generates nearly the same amount of heat through metabolism. An astronaut exposed to the vacuum would not freeze instantly. They would initially feel slightly cold as moisture evaporated from their skin and lungs. They would lose consciousness in about 15 seconds due to lack of oxygen. They would die within a minute or two from asphyxiation. But freezing? That would take hours. The body would cool slowly through radiation, gradually approaching thermal equilibrium with its surroundings. This is nothing like the instant deep freeze of Hollywood. Now let us consider the temperature of space itself. When scientists say that space has a temperature of about 2.7 Kelvin, what do they actually mean? They are referring to the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the entire universe. This radiation has the same spectrum as a black body at 2.7 Kelvin, just a few degrees above absolute zero. An object floating in deep space, far from any stars, would eventually reach equilibrium with this radiation and stabilize at that temperature. But this process takes time. A lot of time. The cosmic microwave background is incredibly dilute. An object cooling toward equilibrium receives very little energy from this radiation. The process is slow, gradual, nothing like the instant freezing of science fiction. Meanwhile, objects in space near stars face the opposite problem. They get too hot. Spacecraft in Earth orbit experience temperature swings of over 500 degrees Fahrenheit between their sunlit and shadowed sides. The side facing the sun can reach over 200 degrees Fahrenheit. The side facing away can drop to negative 200. These extremes occur not because space is cold, but because there is no air to buffer the temperature, no atmosphere to distribute heat. Each side of the spacecraft reaches radiative equilibrium with whatever it faces. Sunlit side roasts, shadowed side chills. The International Space Station maintains comfortable temperatures inside through careful thermal management. Reflective coatings, radiator panels, and active cooling systems work constantly to balance the heat flowing in from sunlight against the heat radiating away into darkness. The challenge is not heating the station. The challenge is preventing it from overheating. All the electrical equipment, all the human bodies, all the sunlight streaming through windows generate heat that must be dumped into space through radiators. In Earth orbit, staying cool is harder than staying warm. The Moon provides a dramatic example. The lunar surface reaches about 250 degrees Fahrenheit at noon. Sunlight bakes the regolith without any atmosphere to scatter the heat. At night, temperatures plunge to negative 280 degrees Fahrenheit. The Moon loses heat rapidly through radiation because there is no atmosphere to trap warmth. The temperature swing is nearly 550 degrees between lunar day and lunar night. Not because space is cold, but because there is nothing to moderate the extremes. Mercury, the closest planet to the Sun, shows similar behavior. Its daytime temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead, but its nighttime temperatures drop to negative 290 degrees. The lack of atmosphere means nothing shields the surface from solar radiation during the day and nothing retains heat during the night. What about the coldest places in the universe? Where do you find genuine, extreme cold? The answer is surprising. Some of the coldest natural places we know of are the dark craters near the Moon's south pole. These permanently shadowed regions never see sunlight. They have been losing heat through radiation for billions of years. Scientists measuring temperatures in these craters have found readings as low as 33 Kelvin, negative 400 degrees Fahrenheit, colder than anywhere else measured in our inner solar system. But even colder places exist. The Boomerang Nebula, a dying star about 5,000 light-years from Earth, contains gas that has been measured at roughly 1 Kelvin. This is colder than the cosmic microwave background. The gas is cold because it is expanding rapidly, cooling through a process similar to the way spray from an aerosol can feel cold. This is among the coldest natural temperatures ever measured. Meanwhile, in laboratories on Earth, scientists have created temperatures far colder than anything found in nature. Using laser cooling and magnetic traps, researchers have achieved temperatures measured in billionths of a Kelvin. These are the coldest conditions in the known universe, created intentionally in controlled environments. Space, for all its reputation as a freezing wasteland, cannot compete with a well-equipped physics laboratory. So let's correct the misconception. Space is not inherently cold. Space is mostly empty, which means temperature is often poorly defined. Near stars, the sparse particles that exist can be extremely hot. Objects in space reach temperatures based on their balance between incoming radiation and outgoing radiation. This can result in extreme heat, extreme cold, or anything in between depending on circumstances. An astronaut exposed to vacuum would not freeze instantly. They would die from decompression and lack of oxygen long before they had time to freeze. The science fiction image of frost forming on eyeballs within seconds is pure invention. Heat leaves the body too slowly through radiation for rapid freezing to occur. The universe is more nuanced than the simple hot-cold dichotomy we imagine. Some of its hottest places and its coldest places are found relatively near each other, separated only by whether sunlight reaches them. Temperature in space is a game of radiation balance, not some ambient chill pervading the void. We have now examined 4 major misconceptions about the universe. The Big Bang that was not a bang, the black holes that do not suck, the sun that is not yellow, the space that is not cold. Each of these beliefs seems so obvious, so fundamental, that questioning them feels almost silly. Yet each is wrong, but we have only scratched the surface. Let us now turn to something closer to home. A structure on our own planet that carries one of the most persistent myths in all of popular culture. They told you the Great Wall of China could be seen from space. They were wrong. Chapter 5. The Great Wall of China cannot be seen from space. How many times have you heard this? The Great Wall of China is the only man-made structure visible from space. It appears in textbooks. Documentary narrators repeat it with authority. Teachers tell students. Parents tell children. This fact has circulated so widely for so long that questioning it seems almost absurd. Surely something must be visible from space, and if anything is, it should be the largest construction project in human history. A wall spanning thousands of miles across mountains and deserts. A monument so vast it took centuries to build. There is just one problem. It is completely false. The Great Wall of China is not visible from space with the naked eye, not from low Earth orbit, certainly not from the moon. Astronauts have tried to see it and failed. China's first astronaut specifically looked for it and could not find it. NASA has confirmed this repeatedly. The myth that has circulated for nearly a century is simply wrong. Let us start by defining what we mean by space. If we're talking about low Earth orbit, where the International Space Station circles at roughly 400 kilometers altitude, the claim is theoretically possible but practically false. If we're talking about the Moon, roughly 380,000 kilometers away, the claim is so physically impossible that believing it requires abandoning basic optics. The origin of this myth traces back surprisingly far. In 1754, the English antiquarian William Stukeley wrote that the Great Wall makes a considerable figure upon the terrestrial globe and may be discerned at the Moon. Remember, this was more than 2 centuries before humans reached space. Stukeley could not possibly have verified this claim. It was pure speculation, fantasy. Yet the idea persisted. By the early 20th century, the myth had become established, fact in popular imagination. A 1932 Ripley's Believe It or Not cartoon claimed the wall is the mightiest work of man and the only one that would be visible to the human eye from the moon. This assertion, repeated confidently decade after decade, became so embedded in culture that few thought to question it. Then humans actually went to space, and the myth began to unravel. Apollo astronauts reported that the Earth from the moon appears as a beautiful sphere, mostly white clouds, some blue ocean, patches of yellow desert, occasional green vegetation. No man-made structures are visible, not cities, not highways, certainly not walls. The idea that you could see a structure on Earth from the moon, a distance of nearly 400,000 kilometers, is optically ridiculous. Consider the mathematics. The Great Wall varies in width, but averages perhaps 5 to 8 meters across at its widest points. To resolve an object, your eye needs that object to subtend a minimum angle. The human eye can resolve details down to about 1 arc minute under optimal conditions. From the moon's distance to see the Great Wall would require visual acuity approximately 17,000 times better than what the human eye possesses. You would essentially need telescope vision at the superhuman level. But what about from low Earth orbit? Here the claim becomes slightly less absurd but still false. The International Space Station orbits at about 400 kilometers altitude. From there, theoretical optical resolution would allow objects of a few meters to be distinguished under perfect conditions. The Great Wall is a few meters wide. Perhaps it could just barely be seen. Astronauts say no. Multiple astronauts from multiple countries have searched for the Great Wall from orbit and been unable to locate it. The problem is not just size, it is contrast. The wall is built primarily from stone and compacted earth. These materials have essentially the same colour as the surrounding landscape. There is no bright paint, no reflective surface, nothing to distinguish the wall from the terrain through which it passes. Jeff Hoffman flew 5 space shuttle missions between 1985 and 1996. He specifically looked for the Great Wall and never found it. The problem, he explained, is that the human eye is most sensitive to contrast. The colour of the wall is not that different from the ground on either side of it. China's first astronaut, Yang Liwei, orbited Earth 14 times in 2003. He was asked about the Great Wall upon his return. His answer was definitive. The Earth looked very beautiful from space, but I did not see our Great Wall. If anyone had national pride as a motivation to spot the wall, it would be China's first taikonaut. He tried. He failed. There have been a few claimed sightings that generate controversy. In 2004, American astronaut Leroy Chiao photographed a section of Central, Inner Mongolia, from the International Space Station using a digital camera with a 180mm telephoto lens. NASA experts later confirmed that the photograph appears to show the wall, but crucially, Chiao himself admitted he was not sure what he was seeing. The photograph required magnification, enhancement, and expert analysis to identify the wall. This is not the same as seeing it with the naked eye. European Space Agency astronaut Alexander Gerst attempted to photograph the wall in 2018 using an 800mm super telephoto lens. He wrote that it was next to impossible to spot with the naked eye, and still tough even with powerful optics. His photographs show faint traces that might be the wall, but only after searching carefully and knowing exactly where to look. So the claim has been reduced from the Great Wall is the only structure visible from space to, if you know exactly where to look, use powerful magnification, and have perfect conditions, you might be able to photograph something that could be the wall. This is rather different from the popular myth. Meanwhile, what can you actually see from space? Cities are clearly visible, especially at night when their lights blaze against the dark landscape. Major highways appear as straight lines cutting through terrain. Airport runways stand out against their surroundings. Large bridges crossing water, ships and their wakes. The pyramids of Giza, which have better contrast against the desert than the wall has against its surroundings, have reportedly been seen by some astronauts. Greenhouse complexes in Spain, covering hundreds of square kilometres with reflective plastic, are easily spotted. The Great Wall is long but narrow. Length does not help visibility from space. What matters is width and contrast. A highway 10 metres wide is more visible than a wall 6 metres wide that blends into its surroundings. The Three Gorges Dam in China, more than 2 kilometres long and 100 metres wide, is far more visible than the Great Wall despite being a much more recent construction. Think about what this myth claims. A structure that averages perhaps 6 metres wide, built from materials that match the local terrain, running through mountains and deserts where it often follows existing ridgelines and natural contours. This should be more visible than highways, airports, cities and dams. The claim fails basic logic even before astronauts began debunking it. Why did this myth become so persistent? Several factors contributed. The Great Wall genuinely is impressive from a historical and engineering standpoint. It represents one of humanity's largest construction projects. There is something poetically satisfying about the idea that our greatest building achievement would be visible from the ultimate vantage point. The myth flatters human accomplishment. The timing also helped establish the myth. By the early 20th century, people were fascinated by aviation and dreaming of spaceflight. Wondering what would be visible from extreme altitude was a natural question. The Great Wall, already famous, became the default answer. Once established, the claim self-perpetuated. Textbook authors copied from earlier textbooks. Teachers taught what they had learned. The claim acquired authority through repetition rather than evidence. There may also be confusion between seeing and detecting. Radar and satellite instruments can indeed detect the Great Wall. Synthetic aperture radar can identify structures hidden from visible light. But detecting with instruments is fundamentally different from seeing with eyes. The myth claims human visibility. Instrumentation is irrelevant to that claim. The Great Wall myth is particularly instructive because it shows how scientific-sounding claims can persist without scrutiny. This fact sounds specific and testable. It invokes space, which confers a kind of scientific credibility. It mentions a famous landmark. Yet for decades, no one thought to actually check if the claim was true. People assumed that someone somewhere had verified it. They had not. The claim originated before space travel existed. It became established during an era when no verification was possible, and when verification finally became possible, the claim failed. The Great Wall is not visible from space with the naked eye. Multiple astronauts have confirmed this. The physics of optics makes the claim implausible from the start. Yet the myth persists because it sounds good and people want to believe it. We are now halfway through our journey of cosmic corrections. The Big Bang was not a bang. Black holes do not suck. The sun is not yellow. Space is not cold. The Great Wall cannot be seen from space. Each myth peeled back reveals a universe more subtle and more interesting than the simplified version we learned. But perhaps no myth is more poetically wrong than the one about our closest, celestial neighbour. Pink Floyd immortalised it in one of the greatest albums ever recorded. Generations have pondered its mysteries. They call it the dark side of the moon, and they are completely, utterly wrong about what that phrase means. Chapter 6, There is No Dark Side of the Moon, 1973. Pink Floyd releases an album that will become one of the best-selling records in history, The Dark Side of the Moon. The title evokes mystery, shadows, hidden realms beyond our perception. It captures something deeply human about our relationship with the cosmos. There are things we cannot see, territories we cannot visit, darkness lurking just beyond the edge of knowledge. The album is a masterpiece, the phrase is a myth. There is no dark side of the moon, not in the way most people imagine it. The far side of the moon receives just as much sunlight as the near side. It is not perpetually shrouded in shadow. It is not colder or darker or more mysterious in any physical sense. The phrase dark side conjures images of eternal night, a frozen wasteland where the sun never shines. This image is completely false. To understand why this misconception exists, we need to understand something called tidal locking. The moon orbits Earth roughly once every 27.3 days. By coincidence, or rather by gravitational physics, the moon also rotates on its axis once every 27.3 days. These two periods match exactly. The result is that the same face of the moon always points toward Earth. We see the near side, we never see the far side, not with the naked eye from Earth's surface anyway. This phenomenon is not unique to our moon. It is common throughout the solar system. Tidal forces from a larger body gradually slow the rotation of a smaller body until the rotation period matches the orbital period. Mercury is tidally locked to the Sun. Most major moons in the solar system are tidally locked to their parent planets. It is a natural consequence of gravitational interaction over millions of years. Because we always see the same face of the moon, we naturally thought of the other face as hidden, unknown, dark. Before the space age, no human had ever seen the far side. It was one of the genuinely mysterious territories in our solar system. What features lurked there? Were they different from the near side? We could only speculate. The mystery was solved in 1959. The Soviet spacecraft Luna 3 flew behind the moon and transmitted the first photographs of the far side. The images were grainy and low resolution by modern standards, but they revealed something unexpected. The far side looks dramatically different from the near side. It is covered with craters. Dense, overlapping impact basins pock the surface everywhere you look. In contrast, the near side has large, dark regions called maria, Latin for seas, which early astronomers mistakenly thought were oceans. The maria are actually ancient lava flows. Billions of years ago, impacts created enormous basins on the moon's surface. Volcanic activity later filled these basins with dark, basaltic lava. The near side has many maria. The far side has almost none. Only about 1% of the far side is covered by maria compared to over 30% of the near side. This asymmetry is still being studied by scientists today. The leading theories involve differences in crustal thickness and the heat distribution inside the moon. But none of this has anything to do with darkness or light. The far side gets exactly as much sunlight as the near side. Think about it. The moon orbits Earth. As it orbits, the sun illuminates it from different angles. During a full moon as seen from Earth, the The entire near side is lit by the sun, but this means the far side is in darkness, experiencing lunar night. 2 weeks later, during a new moon as seen from Earth, the situation reverses. The near side faces away from the sun and experiences darkness. The far side is fully illuminated. Every location on the moon, whether on the near side or the far side, experiences roughly 2 weeks of daylight, followed by 2 weeks of night. The cycle continues endlessly. There is no region that remains in permanent darkness, no place where the sun never shines. The far side is only dark in the sense of unknown or unseen. It is not dark in the sense of unlit. The terminology has confused people for generations. When someone says dark side, most listeners imagine physical darkness, absence of light, cold and shadow. The metaphorical meaning of dark, referring to mystery and ignorance, has been lost. People think the far side is literally dark, permanently, always. China's Chang'e 4 mission landed on the far side in 2019. The photographs it transmitted show a landscape bathed in sunlight. Bright, harsh. Shadows are sharp and black because there is no atmosphere to scatter light. The sky is black even in daylight because there is no air to create blue. But the surface is brilliantly lit. The sun shines on the far side exactly as it shines on the near side. There is one sense in which far side could be considered darker, but it has nothing to do with sunlight. The near side of the moon receives earth shine. When the sun is not directly illuminating the near side, light reflected from Earth provides some illumination. This is why you can sometimes see the full disk of the moon, faintly, even when only a crescent is sunlit. The ghostly glow of the rest of the disk is earthshine. The far side never experiences earthshine. It always faces away from Earth by definition. So during lunar night on the far side, the only light comes from stars. The darkness is more complete than on the near side. But this is a subtle effect during nighttime only. It does not mean the far side is always dark or even usually dark. It just means the nights are darker. Astronomers and scientists prefer the term far side precisely to avoid the confusion caused by dark side. The far side is far. It is on the opposite side from Earth, but it is not dark. The terminology matters because it shapes how people think about our cosmic neighborhood. Consider the implications if the dark side myth were true. If one hemisphere of the moon never received sunlight, its temperature would drop toward absolute zero. Ice would accumulate. The contrast between the frozen dark side and the sun-baked near side would be extreme. The moon would be a world of fire and ice split down the middle by an eternal terminator line. This is not what we observe. The moon has temperature variations based on day and night cycles, just like Earth. The difference is that lunar days are about 29 Earth days long. Each location bakes for 2 weeks under the sun and then freezes for 2 weeks in darkness. This happens everywhere on the moon. Near side, far side, equator, poles. The pattern is the same. There is one exception. At the lunar poles, in the bottoms of deep craters, there are small regions of permanent shadow. The sun never rises high enough at the poles to illuminate the floors of certain craters. These permanently shadowed regions are genuinely dark. They are also genuinely cold, reaching temperatures near 40 Kelvin, among the coldest places in the inner solar system. Ice has been detected in some of these regions, preserved for billions of years in eternal shade. But these permanently shadowed craters are a tiny fraction of the lunar surface. They exist at both poles. They are not unique to the far side. They are special local features, not a characteristic of an entire hemisphere. The dark side myth implies half the moon is always dark. The reality is that only a few scattered crater floors never see sunlight. Pink Floyd was not making a scientific claim. The dark side of the moon is a meditation on madness, mortality, and the human condition. The title is metaphorical. The dark side represents the hidden parts of the psyche, the aspects of ourselves we do not show the world, the fears and pressures that lurk beneath surface sanity. As art, the metaphor works beautifully, but metaphors can become misleading when they escape their original context. Dark side entered common speech as a way to describe the far side of the moon. People forgot the metaphorical origin and took the phrase literally. Generations grew up believing that half our moon never sees the sun. This belief persists despite decades of lunar exploration proving otherwise. The far side of the moon is fascinating for many reasons that have nothing to do with darkness. Its heavily cratered surface tells a different geological story than the near side. Its lack of maria suggests different volcanic history. Its isolation from Earth makes it an ideal location for radio astronomy, shielded from the electronic noise of human civilization. Scientists have proposed building radio telescopes in far side craters to listen for signals that Earth's electromagnetic pollution would otherwise drown out. The far side is also a potential site for future human bases. While communication with Earth would require relay satellites, the far side offers unique scientific opportunities. Every sunrise and sunset there marks a transition that humans have never directly witnessed. Standing on the far side, you would never see Earth in the sky. Our home planet would be permanently hidden below the horizon. That psychological isolation is something no human has ever experienced. So let us correct the myth once and for all. There is no dark side of the moon. There is a far side. It receives exactly as much sunlight as the side we see. The phrase dark side originally meant unknown or hidden, not unilluminated. The metaphor was poetic, but the literal interpretation is wrong. We have now corrected 6 cosmic myths, but perhaps the most personal myth on our list concerns not the distant moon or distant stars, but something far closer. Something you carry with you every moment of every day. Your brain. They told you that you only use 10% of it. They lied. Chapter 7. You use all of your brain. Imagine having unlimited potential, 90% of your brain sitting idle, waiting to be activated. If only you could tap into those dormant regions, you could become a genius, develop telekinetic powers, remember everything you have ever seen, learn languages in days. The possibilities would be endless. This fantasy has powered self-help books for decades. It drives the plots of science fiction movies like Limitless and Lucy. Motivational speakers invoke it to convince you that greatness lies dormant within your skull. The claim sounds scientific, specific, 10%, not 8 or 12, exactly 10. Surely someone measured this. No one did. The 10% myth is completely false. You use your entire brain, and you have been using your entire brain your whole life. The idea that vast regions of neural tissue sit dormant waiting to be activated is not just wrong, it is biologically absurd. Let us trace the origin of this myth. Unlike some misconceptions that have ancient roots, the 10% myth appears to be relatively modern. Its exact origin is unclear, but several candidates have been proposed. One popular attribution points to William James, a pioneering psychologist who wrote in 1907 that we are making use of only a small part of our possible mental and physical resources. Notice what James actually said. He claimed we underuse our potential. He said nothing about brain percentage. He made no measurement. He was motivating people to achieve more, not describing neural anatomy. Somewhere between James's vague claim and modern popular culture, small part became 10% and possible resources became brain. Another possible origin involves early neuroscience. In the 1930s, researchers discovered that electrically stimulating certain brain regions produced observable responses, while stimulating other regions produced nothing apparent. These silent regions were initially mysterious. What were they doing? If stimulating them caused no visible effect, perhaps they were inactive, unused. We now know these regions are association cortex. They integrate information from multiple brain areas. They handle our most sophisticated cognitive functions: abstract thinking, planning, language comprehension, self-awareness. They do not produce simple observable responses to electrical stimulation because their functions are complex, but they are absolutely essential. Damage them, and you lose the very capacities that make you human. The myth may also stem from the discovery that glial cells outnumber neurons by a significant margin. Early estimates suggested about 10 neurons for every 90 glial cells. If only neurons matter, someone might conclude we use only 10% of our brain cells. But this reasoning fails on multiple levels. Glial cells are not inactive filler. They support neurons, insulate axons, regulate the brain's chemical environment, and participate in neural signaling. They matter. And the ratio turns out to be closer to 1:1 anyway. The 10:1 estimate was wrong. Whatever its origin, the 10% myth took hold in popular culture and refused to let go. Surveys consistently show that large majorities of people believe it. Even teachers perpetuate it in classrooms. The myth appears in advertising, movies, television shows, and books. It has become one of the most widespread misconceptions about human biology. The evidence against the myth is overwhelming. Modern brain imaging techniques allow us to observe neural activity in living brains. Functional MRI scans show which regions are active during various tasks. Positron emission tomography reveals metabolic activity throughout the brain. What do these scans show? The entire brain is active. Not all regions at once in equal measure, but every region shows activity over the course of a day. Even during sleep, significant brain activity continues. The brain is never 90% dark. It is a constantly buzzing network of interconnected neurons processing information even when you're not consciously aware of it. Consider the energy argument. The human brain accounts for roughly 2% of body weight, but consumes about 20% of the body's energy. In infants, the brain consumes up to 60% of total energy. Evolution is ruthlessly efficient. An organ that uses 20% of your calories would never be allowed to sit 90% idle. Natural selection would have shrunk it long ago. The metabolic cost of a brain this size only makes sense if the brain is fully utilized. Consider the damage argument. If 90% of the brain were inactive, brain damage would rarely cause problems. Strokes, tumors, and injuries would usually hit unused regions. The patient would be fine. We observe the exact opposite. Brain damage almost always causes functional deficits. Damage to different regions causes different specific problems: loss of language, loss of memory, loss of motor control, loss of emotional regulation, loss of vision. The mapping between brain regions and functions has been extensively documented. No region is expendable, no region is unused. Consider the structural argument. The brain is organized into distinct regions with specific functions. The visual cortex processes visual information. The motor cortex controls movement. The prefrontal cortex handles executive functions. Broca's area processes speech production. Wernicke's area processes speech comprehension. The hippocampus consolidates memory. The amygdala processes emotion. Every region has a job. Decades of neurological research have mapped these functions in detail. Where is the unused 90% supposed to be? Consider the evolutionary argument. The brain is metabolically expensive to grow and maintain. Childbirth is difficult partly because human heads are so large. If most of the brain were unnecessary, evolutionary pressure would have selected for smaller brains long ago. The fact that humans have such large, energy-hungry brains suggests that all of that tissue is doing something important. The 10% myth persists because it is appealing. It suggests untapped potential, hidden powers waiting to be unlocked. It provides hope that we could be more than we are. Self-help gurus exploit this hope. They promise techniques to access that dormant 90%. Brain training games, meditation methods, dietary supplements. None of them work because there is no dormant 90% to activate. This does not mean we cannot improve our cognitive abilities. Learning new skills creates new neural connections. Education expands knowledge and capabilities. Mental and physical health affect brain function. There is real potential for growth and improvement. But this growth happens through using more of your brain's existing capacity more effectively, not through activating previously unused tissue. The movies get it spectacularly wrong. In Limitless, a drug allows the protagonist to access 100% of his brain, and he becomes virtually superhuman. In Lucy, the title character gains telekinesis and time manipulation as she approaches full brain usage. These are entertaining fantasies, but they bear no relationship to neuroscience. You already use 100% of your brain. Where are your telekinetic powers? In reality, we use different parts of our brain for different tasks. Reading activates visual processing regions, language regions, and memory regions. Playing music activates motor regions, auditory regions, and areas involved in timing and rhythm. Doing math activates regions associated with numerical processing and spatial reasoning. No single task activates the entire brain simultaneously because different tasks require different specialized systems. But over the course of a day, every region gets used. Brain imaging studies that track activity over extended periods show no dark zones, no permanently silent regions. The brain is always working even during sleep. Dreams involve neural activity across multiple brain regions. Memory consolidation occurs while we sleep. The brain repairs and maintains itself. It is never idle. The persistence of this myth says something troubling about scientific literacy. A claim that contradicts everything we know about biology and neuroscience has remained popular for nearly a century. People believe it because it sounds scientific and because they want it to be true. Critical thinking would reveal the absurdity of the claim in minutes. An energy-hungry organ that evolution ruthlessly optimizes would never be 90% dormant. Yet the myth persists. You are already using your whole brain. The potential for growth comes not from activating unused regions, but from strengthening connections, learning new information, developing new skills, and maintaining brain health. The truth is less dramatic than the myth, but more empowering. Your brain is a fully operational marvel of biological engineering, working constantly to navigate the world, and you've been using all of it since the day you were born. We have demolished 7 myths now. From cosmic origins to human neuroscience, the lies we have been told span incredible scales. But let us return to the cosmos for our 8th revelation, to a misconception so dramatic that Hollywood has built entire franchises around it. The sound of space battles, the roar of exploding starships, the scream of engines in the void. In space no one can hear you scream. And that famous tagline is actually true. Chapter 8, In Space You Cannot Hear Anything, 1977. A movie opens with a Star Destroyer rumbling across the screen, engines, thundering, lasers blazing. Star Wars changes cinema forever. Audiences thrill to the sound of TIE fighters screaming through space. X-Wings roar as they engage in dogfights. The Death Star explodes with a cataclysmic boom that shakes theatre seats. The sound design is iconic, memorable, visceral. It is also physically impossible. 2 years later, a different approach. Alien. The tagline appears on screen. In space, no one can hear you scream. This is not just marketing. It is physics. And unlike most things Hollywood tells us about space, this one happens to be true. Sound cannot travel through a vacuum. This is not a technical limitation that future technology might overcome. It is a fundamental property of what sound actually is. Sound is a mechanical wave, a compression and rarefaction of matter propagating through a medium. When you speak, your vocal cords vibrate. They push against air molecules, which push against adjacent air molecules, which push against more air molecules, creating a wave of compression that travels outward. When that wave reaches someone's ear, it vibrates their eardrum. The brain interprets those vibrations as sound. No matter, no sound. It is that simple. Sound requires something to compress, something to vibrate, something to carry the wave from source to listener. In the vacuum of space, there are too few particles to sustain a sound wave. The wave has nothing to propagate through. It dies at its source. Consider numbers. The air you're breathing right now contains roughly 10 billion molecules per cubic centimetre. That is a lot of molecules bumping into each other. Sound waves travel through this dense medium at roughly 340 metres per second. Now consider space. Interplanetary space contains perhaps 5 particles per cubic centimetre. That is 15 orders of magnitude less dense. 15 zeros difference. In interstellar space, the density drops to 1/10 of a particle per cubic centimetre. In the voids between galaxies, it drops to roughly 1 particle per cubic metre. These densities are so low that any sound wave would dissipate instantly. There simply are not enough particles to sustain the compression and rarefaction cycle. A scream in space would not propagate beyond your own helmet. The vibrations would stay trapped in whatever medium immediately surrounds your mouth. This means every space battle you have ever seen in movies is wrong. Explosions in space are silent. Ships colliding make no sound. Laser blasts, whatever those actually are, produce no noise as they travel through vacuum. The dramatic soundscapes of Star Wars, Star Trek, Battlestar Galactica, and countless other franchises are pure invention. Entertaining invention, certainly. But invention nonetheless. Filmmakers know this. They include sound anyway because silent space battles are cinematically boring. The visceral impact of rumbling engines and exploding starships enhances emotional engagement. Accuracy is sacrificed for entertainment. Most audiences neither know nor care about the physics. They came for the experience, not the science lesson. But the physics matter if you want to understand the universe as it actually is. Space is silent. Profoundly, utterly, eternally silent. The cosmos makes no noise because there is nothing to carry noise between the stars. Or does it? Here we encounter an interesting nuance. Space is not a perfect vacuum. Those few particles per cubic centimetre are not zero particles, they are matter. And matter can, in principle, carry compression waves. Could sound exist in space after all? Technically yes, but not in any way you could hear. For sound to propagate, you need enough particles close enough together that they can bump into each other and pass vibrations along. In the extremely thin medium of interstellar space, particles are so far apart that any compression wave would have to have an enormously long wavelength. We are talking wavelengths measured in light years, frequencies so low they cycle once over millions of years. These are not sounds in any meaningful human sense. You could not hear them. You could not even detect them with ordinary instruments. NASA announced in 2022 that they had recorded sound from a black hole. Headlines proclaimed that black holes make spooky sounds. What actually happened? Researchers used data from the Chandra X-ray Observatory to detect pressure waves rippling through the hot gas surrounding a supermassive black hole in the Perseus galaxy cluster. These pressure waves had a frequency of about one cycle every 10 million years. That is roughly 57 octaves below the lowest note a human ear can detect. To make it audible, scientists scaled the frequency up by a factor of 288 quadrillion. What you hear in those recordings is a mathematical translation, not actual sound. The key point is that the gas surrounding the black hole is dense, enough to carry pressure waves. The black hole itself is not in vacuum. It sits at the center of a cluster filled with hot intergalactic gas. In that medium, compression waves can propagate. But this is a special case. Most of space is too empty for any sound to travel. What would you actually experience in space? Imagine you're an astronaut on a spacewalk. Your helmet contains air. You can hear your own breathing, your voice, any sounds transmitted through your suit's speakers. If you bang a tool against the outside of your spacecraft, you hear nothing directly. No air to carry the sound. But the vibrations travel through the metal of the ship and potentially through your gloved hands to your body. Sound can conduct through solid materials even in vacuum. You might feel the impact more than hear it. Two astronauts floating in space a few meters apart could not talk directly. Their voices would not carry across the gap. This is why spacesuits have radios. Radio waves are electromagnetic radiation, not mechanical waves. They travel through vacuum at the speed of light. Astronauts communicate by converting sound to radio and back to sound again. If a spaceship exploded near you in vacuum, you would see the flash. You would feel the heat radiation. Debris might hit you, but you would hear nothing. The expansion of gases would occur in silence. Any secondary explosions, silent. The catastrophic death of a spacecraft would be eerily quiet. Just light and motion and debris flying outward without a sound. This silence extends to all scales. Stars explode with the energy of billions of nuclear bombs. Supernovae brighten entire galaxies. The violence is unimaginable. But it is silent. There is no medium to carry the sound from a supernova to observers light years away. The most dramatic events in the universe occur without making a sound that could ever reach us. Galaxies collide over millions of years, billions of stars passing through each other in a cosmic dance, silent. Black holes merge with the violence of space-time itself tearing and reforming. The energy release is immense, but there is no sound, only gravitational waves rippling outward through the fabric of space, detectable by sensitive instruments but not audible to ears. The silence of space is profound. We are accustomed to sound as a constant companion. Even in quiet rooms, we hear air conditioning, distant traffic, our own heartbeat. True silence is rare on Earth. Space offers true silence. The kind of silence where there is genuinely nothing to hear because there is no medium to hear anything through. Some find this isolating, others find it peaceful. Astronauts describe looking out at the universe and feeling a sense of calm that comes from the absence of noise. No distractions, no background hum, just the pure visual spectacle of stars and galaxies against the perfect black of an airless void. Science fiction usually gets this wrong for good reason. Sound is emotional. It connects viewers to the action on screen. Silent space battles would feel distant and disconnected. Filmmakers make a conscious choice to sacrifice accuracy for engagement. But knowing the truth adds a different kind of appreciation. The universe we live in is stranger and quieter than fiction typically portrays. There is one more nuance worth mentioning. Sound cannot travel between objects in vacuum, but sound can exist inside objects in vacuum. The sun roars with the energy of millions of hydrogen bombs detonating every second. That energy creates pressure waves inside the sun. Solar physicists study these waves, a field called helioseismology. By observing how the sun's surface vibrates, they can deduce information about its internal structure. The sun makes sound. That sound just never escapes into the vacuum surrounding it. The silence of space is a feature, not a bug. It makes radio astronomy possible. The cosmos speaks to us in radio waves, X-rays, infrared, and visible light because electromagnetic radiation travels through vacuum. If space were filled with a sound-transmitting medium, the noise would be overwhelming. The roar of every star, every explosion, every violent event would drown out everything else. We would be deaf to the universe's whispers. So the next time you watch a space battle in a movie, enjoy the sound effects for what they are. Entertainment, artistic license, a necessary fiction to make the experience engaging. But remember that the real universe operates in eternal silence. The most violent explosions make no sound. The largest structures form without a whisper. Space is quiet, not because nothing is happening, but because there is nothing to carry the vibrations. We approach the end of our journey now. 2 more myths remain. Both concern the structure of the cosmos itself. First, the asteroid belt that movies portray as a dense, dangerous obstacle course. Second, the center of the universe that does not exist. Let us venture into the belt of rocks between Mars and Jupiter and discover the truth about cosmic emptiness. Chapter 9. The asteroid belt is almost completely empty. The Millennium Falcon plunges into an asteroid field. Rocks tumble and spin in every direction. Han Solo banks hard left, then hard right, threading through gaps barely wider than his ship. TIE fighters pursue, crashing into boulders when they cannot match his piloting skill. Never tell me the odds, he says. The scene is iconic, tense, thrilling, and completely divorced from reality. The asteroid belt is not a dense obstacle course. It is not a field of tumbling boulders requiring skilled navigation. It is not dangerous to traverse. The asteroid belt is almost entirely empty space. Spacecraft have passed through it multiple times without incident. In fact, without trying very hard, you would never hit anything. Let us understand what the asteroid belt actually is. Between the orbits of Mars and Jupiter lies a region of space roughly 150 million kilometers wide. Within this region orbit millions of rocky objects ranging from dust particles to the dwarf planet Ceres at 950 kilometers across. This sounds crowded. Millions of objects. It sounds like exactly the dense field that movies portray. But consider the scale. The asteroid belt spans a volume of approximately 2.5 times 10 to the 25th cubic kilometers. That is a number so large it loses all intuitive meaning. Within this unimaginably vast volume, all the asteroids combined contain less than 4% of the mass of our moon. If you gathered every asteroid and compressed them into a single body, you would have an object less than 1,500 kilometers across, smaller than our moon. The asteroids are not numerous in any meaningful sense relative to the space they occupy. They are scattered, isolated, lonely. The average distance between asteroids larger than 1 kilometer is several 100,000 kilometers. To put that in perspective, the distance from Earth to the Moon is about 384,000 kilometers. In the asteroid belt, you would need to travel roughly that far on average to encounter another rock of appreciable size. If you were standing on one asteroid and looked around, you would not see a sky full of threatening boulders. You would see stars. The nearest visible asteroid would appear as a dim point of light, if you could see it at all. This is not speculation, this is what we have observed. Pioneer 10 was the first spacecraft to traverse the asteroid belt, passing through in 1972. At the time, mission planners were genuinely concerned about collisions. They did not know how dense the belt might be. Could dust and debris damage the spacecraft? Would larger rocks pose a threat? They sent Pioneer 10 through and held their breath. Nothing happened. Pioneer 10 passed through the asteroid belt without incident. So did Pioneer 11. So did Voyager 1 and Voyager 2. So did Galileo on its way to Jupiter. So did Cassini on its way to Saturn. So did New Horizons on its way to Pluto. So did Juno on its way to Jupiter. More than a dozen spacecraft have traversed the asteroid belt. None has hit anything. None has even come close to hitting anything by accident. The odds of a spacecraft colliding with an asteroid in the belt are estimated at less than 1 in a billion. You have better odds of being struck by lightning multiple times in a single day. The asteroid belt is not a hazard. It is a vast emptiness with some scattered rocks that you would have to actively seek out to encounter. NASA's Dawn mission actually wanted to visit asteroids in the belt. This required careful trajectory planning because the asteroids are so far apart. Dawn visited Vesta in 2011 and Ceres in 2015, becoming the first spacecraft to orbit 2 different bodies beyond Earth. The mission succeeded not because Dawn skillfully navigated through dense rock fields, but because Dawn was precisely targeted towards specific objects in a mostly empty region of space. The misconception about asteroid density comes primarily from visual media. Movies and television shows need drama. A sparse field of distant objects is not dramatic. A dense, tumbling chaos of rocks provides tension, excitement, visual spectacle. Filmmakers compress the asteroid belt into something manageable and dangerous because sparse accuracy does not serve the story. Video games follow the same pattern. Asteroid field levels feature dense clusters of rocks to shoot or avoid. The gameplay would be boring if asteroids were realistic distances apart. You would fly for hours through empty space, see nothing, encounter nothing. That is accurate but not fun. Science fiction literature often does better, acknowledging the emptiness of the belt, but visual media dominates public perception. Most people have never read hard science fiction descriptions of asteroid mining or belt colonization. They have seen Star Wars and video games. The dense obstacle course version becomes the default mental image. There is also a linguistic issue. We call it a belt, which suggests a continuous band. Belts are solid objects wrapped around a waist. The imagery suggests density, continuity, substance. A more accurate term might be asteroid region or asteroid zone. But belt became the standard terminology early in astronomical history, and it stuck. Consider what the asteroid belt actually looks like from a spacecraft passing through. First, you see nothing unusual. Stars appear exactly as they do elsewhere. The sun shrinks to a bright point as you travel outward, but it is still clearly the dominant light source. The outer planets are distant points of light, if visible at all. You pass through millions of kilometers of apparently empty space. If you are very observant, with good instruments, you might detect a slight increase in zodiacal light, the faint glow of sunlight reflecting off interplanetary dust. The asteroid belt does have more dust than surrounding regions, but this is subtle. You would not notice it without instruments. Days pass. Weeks. You continue through the belt. Where are the asteroids? They are out there, hundreds of thousands of kilometers away, invisible points lost in the vastness. Your spacecraft's navigation system might flag a few larger asteroids in the general vicinity, but general vicinity in space means distances that would span the Earth-Moon system multiple times. Eventually you exit the belt and approach Jupiter. The whole transit, which might take months or years depending on trajectory, involved no asteroid avoidance maneuvers because there was nothing to avoid. The dramatic weaving and dodging of science fiction exists only in fiction. This emptiness has implications for future human activity in space. Science fiction often portrays asteroid mining as a dangerous occupation, with miners dodging between tumbling rocks to extract precious metals. The reality would be very different. Miners would travel to specific asteroids identified by survey missions. They would work on isolated bodies with no other asteroids visible to the naked eye. The danger would come from the asteroids themselves, low gravity, sharp edges, dust and radiation exposure, not from collisions with other asteroids. Belt colonization, if it ever happens, would involve tiny habitats separated by enormous distances. Communication delays would be significant. The nearest neighbour might be weeks of travel away. It would be one of the most isolated environments humans could inhabit. Not a crowded frontier, but a sparse scattering of outposts in an ocean of nothing. The asteroid belt is a fascinating region for scientific study. It preserves material from the early solar system. Asteroids are remnants of planetesimals that never combined into a planet, largely because Jupiter's gravity stirred them up and prevented accumulation. Different asteroids have different compositions: carbonaceous, silicate, metallic, reflecting the diversity of conditions in the early solar nebula. But scientifically fascinating does not mean densely packed. The belt contains valuable information precisely because it is pristine. Collisions are rare enough that many asteroids have remained essentially unchanged for billions of years. If the belt were as dense as movies suggest, collisions would be constant. Everything would be ground to dust. The belt is geologically quiet because encounters are infrequent. One more point deserves mention. Saturn's rings are sometimes conflated with asteroid belts, but they represent a completely different phenomenon. Saturn's rings are dense. Particles in the rings are separated by meters to kilometers, not hundreds of thousands of kilometers. The rings are visible from Earth because they contain enormous amounts of material in a relatively thin disk. If the asteroid belt were that dense, it would be visible as a band in the night sky. It is not visible because it is not dense. The two structures are fundamentally different despite both being called rings or belts of material. So let us correct the final asteroid myth. The belt is real. The asteroids are real. But the dense, dangerous obstacle course of science fiction is pure fantasy. The asteroid belt is mostly empty space. Traversing it is trivially safe. Finding an asteroid requires intentionally navigating toward one. The drama of asteroid fields exists only in imagination. We have now examined 9 cosmic lies. From the Big Bang to the asteroid belt, from the sun to the moon, from black holes to our own brains. But one final myth remains. Perhaps the deepest misconception of all. It concerns the structure of the universe itself, the center from which everything supposedly exploded, the origin point of all existence. There is no center of the universe, and understanding why will take everything we have learned and push it one step further. Chapter 10. The universe does not have a center. We began this journey with the Big Bang. We return to it now, but from a different angle. We established that the Big Bang was not an explosion. Now we must confront a deeper implication. If there was no explosion, there is no center. The universe has no middle, no edge, no special location from which everything expands. This concept is so counterintuitive that even after explanation most people struggle to accept it. Let us approach this carefully. When we learn about the Big Bang, a natural picture forms in our minds. A tiny point explodes. Matter flies outward in all directions. The universe expands like debris from a bomb. Somewhere out there, at the center of this expansion, lies the point where it all began. If only we could find that point, we would be looking at the birthplace of existence itself. This picture is completely wrong. Remember our balloon analogy from the first chapter? Dots on a balloon represent galaxies. Inflate the balloon and the dots move apart. Here is the key insight we must now fully absorb. Where is the center of the balloon surface? Not inside the balloon, not outside the balloon. On the surface itself there is no center. Every dot sees every other dot moving away. No dot is special. No dot sits at the middle. The surface of the balloon is two-dimensional. It curves through 3 dimensions, but creatures living on the surface experience only 2 dimensions. They cannot point toward the center of the balloon because the center is not on the surface. It exists in a dimension they cannot access. Our universe may work similarly. We experience 3 dimensions of space. The universe may curve through a 4th, spatial dimension that we cannot directly perceive. There may be no point in our 3-dimensional space that counts as the center, because the center, if it exists at all, lies in a dimension beyond our experience. But let us not rely too heavily on the balloon analogy. It has limitations. The universe might not be curved at all. Current measurements suggest the universe is geometrically flat, or very close to flat. A flat universe has no center in any dimension. It extends infinitely in all directions. Every point is equivalent to every other point. There is no middle because there is no edge. Consider what observations tell us. When we look in any direction, we see galaxies receding from us. The farther away they are, the faster they recede. This is Hubble's law, discovered nearly a century ago. It might seem like we are at the center. Everything runs away from us. We must be special. But the same observation would be made from any galaxy in the universe. An astronomer in the Andromeda Galaxy would see us receding along with everything else. An astronomer in a galaxy 1 billion light years away would see all other galaxies, including ours, moving away from them. Everyone sees themselves as stationary while everything else flees. This is exactly what happens when space itself expands. No observer is special. No location is central. Imagine an infinite sheet of rubber with dots marked at regular intervals. Now stretch the rubber uniformly in all directions. Every dot sees every other dot moving away. Dots that start far apart end up very far apart because more rubber stretches between them. Dots that start close together separate by less distance. This is Hubble's law in action. More distant objects recede faster not because they are moving faster through space, but because more space is expanding between you and them. In this picture, where is the center of expansion? There is none. The expansion happens everywhere at once. Every point is equivalent. The universe has no privileged location. This becomes even stranger when we consider the observable universe. We can only see objects whose light has had time to reach us since the Big Bang. This defines a sphere centered on our location. The observable universe is about 93 billion light-years across, and we appear to be at its center. Does this make us special? No. Every observer has their own observable universe centered on themselves. An observer far from Earth has a different observable sphere. Some parts overlap with ours. Some parts lie beyond what we can see while being visible to them. Every observer sits at the center of their own observable universe by definition. The edge of the observable universe is not a physical boundary. It is just the limit of how far light has traveled since the cosmos became transparent. The whole universe, as distinct from the observable universe, might be infinite, or it might be finite but unbounded, like the surface of the balloon. In either case, there is no center. An infinite universe has no middle, because it extends forever in all directions. A finite but unbounded universe has no middle because it curves back on itself. Either way, the question where is the center has no answer. This challenges deep human intuition. We're accustomed to things having middles. A room has a center, a city has a center, a galaxy has a center. Surely the universe must have a center too. But the universe is not like a room, or a city, or even a galaxy. It is the totality of existence, the container of all containers. The rules that apply inside the universe do not necessarily apply to the universe itself. Think about the question, what is north of the North Pole? It sounds like a reasonable question. Everywhere on Earth has something north of it. But the North Pole is different. It is the northernmost point. There is no north beyond it. The question is malformed. It assumes a structure that does not exist at that location. Similarly, asking where is the center of the universe assumes the universe has a structure it does not possess. The universe is not embedded in a larger space. It is all the space there is. There is no outside from which to locate a center. There is no vantage point that reveals the whole structure with a middle you could point to. We began by saying the Big Bang was not an explosion. Now you can see why that matters. Explosions have centers. The debris flies outward from a point of origin. If the Big Bang were an explosion, we could trace the trajectories of galaxies backward and find where they all converge. That convergence point would be the center. But the expansion of space is not like that. Run the expansion backward and everything gets closer together. Every point converges toward every other point. The universe gets denser everywhere simultaneously. At the moment of the Big Bang, the entire universe, however large it was, existed at infinite density. Not at a point in space, but at every point in space. The center was everywhere because everywhere was the same place. This brings us to the deepest resolution of the center question. The Big Bang did not happen somewhere. The Big Bang happened everywhere. Every point in the current universe was at the Big Bang. You are standing at the center of the universe right now. So is everyone else. The center is not a special location. The center is all locations. Or equivalently, there is no center because every point has equal claim to being central. 13.8 billion years ago, the region of space you currently occupy was part of the hot, dense plasma that filled the universe. So was every other region. The entire cosmos shared the same conditions. Since then, space has expanded, carrying galaxies apart like dots on an inflating balloon. But the expansion has no focus, no origin point, no center from which it spreads. This concept is difficult. It defies everyday intuition built from experience with bounded objects. But it is the best description we have of how the cosmos actually works. General relativity, the theory of gravity that describes the universe on large scales, allows for spaces with no center. Cosmological observations confirm that we live in such a space. The universe is homogeneous on large scales, the same everywhere, and isotropic, the same in all directions. A homogeneous isotropic universe has no center by definition. If this makes you uncomfortable, you are in good company. The idea bothered Einstein himself. He initially tried to find a static, eternal universe that avoided these strange implications. He added a cosmological constant to his equations to prevent expansion. When Hubble discovered that the universe actually is expanding, Einstein reportedly called the cosmological constant his greatest blunder. He eventually accepted what the evidence showed. The universe is dynamic, it changes, it expands, and it has no center. So we conclude our journey through 10 cosmic lies with the most fundamental misconception of all. There is no point in space where the Big Bang happened. There is no center of the universe. There is no special location where existence began. The beginning happened everywhere. The center is everywhere. And you, right now, standing on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, are as much at the center of the universe as anywhere else in all of existence. These 10 myths have something in common. They all come from applying human-scale intuition to cosmic-scale reality. Explosions have centers, so the Big Bang must have one. Vacuums suck, so black holes must suck. Yellow is warm and comforting, so the sun must be yellow. Cold is the absence of warmth, so space must be cold. Things have middles, so the universe must have a middle. The cosmos does not care about human intuition. It operates on principles that emerge from physics, mathematics, and the deep structure of reality. Understanding those principles requires abandoning comfortable assumptions. The reward is a universe far stranger, far more beautiful, and far more wondrous than the simplified version we learned as children. You have now heard the truth about 10 cosmic lies. The Big Bang that was not a bang, the black holes that do not suck, the sun that is not yellow, the space that is not cold, the great wall that cannot be seen, the dark side that is not dark, the brain that is fully used, the space that is silent, the asteroid belt that is empty, the universe that has no center. What other lies await discovery? What other assumptions must we question? The cosmos is vast, strange, and endlessly surprising. Every certainty we hold may be another misconception waiting to be demolished by closer examination. That is not frightening. That is wonderful. That is science. If you enjoyed this deep investigation into cosmic truths, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments which misconception surprised you most. Which lie had you believing for the longest, and what other myths about the universe should we investigate next? The universe is not what you were taught. It is stranger, more beautiful, more mysterious, and far, far more interesting than the simplified version that fits on classroom posters. Thank you for watching. I will see you in the next investigation.